Good morning to all of you all. Today we are going to see the difference between a spring and a string. A spring and a string. Well, the first difference, first let us see one similarity before we see the difference. What you must note is that a spring or a string always transmits a force along its length. This is very important. That is, let us say the string is fixed here and you apply a force here like this. This is a string. You apply a force like that. Well, it will not transmit this force. In fact, the string will become straight like that and F will become like this. It will become, let's say, applying the force in the same direction. So the string would become like that and it will transmit the force along its length. Same in the spring also. If you fix a spring at one end and apply a force here, the spring would become like this. That is, it can transmit, both these can transmit a force only along their lengths. This is unlike a rod. Supposing you have a weighing scale and you have pans here. You have pans here. You see the weight which you put here applies a force like this on the rod. This is a rod and is able to transmit it to this. And these forces are not along the length of the rod. So this is one very important difference. So in fact, when we mark forces on a string or a spring, it has to be always along its length. That's very important. But for a rod, it need not be along its length. Now, another thing we can see. Now we go to the differences between the spring and the string. You can only pull with a string. You cannot push with a spring. Suppose you are going for a walk with your dog and there is a chain. You cannot push the dog with it. Yes, you can only pull it. So a string transmits only a pulling force. There is no pushing force in a string. Whereas a spring which is there, you can push as well as pull with a spring. If you pull a string, it pulls you back. Similarly, if you pull a spring, it pulls you back. If you push a spring, it pushes you back. This is by the Newton's third law. Then, another important difference is that a string can transmit a force without any distortion. An ideal string, if you take inextensible string, it can transmit a force without distortion. That is almost immediately, instantaneously. But if you take a spring, it is a bit slow because unless it gets distorted, that is, unless it gets extended or compressed, it will not transmit a force. So you find that the spring which is there is slow, it is sloppy. Whereas a string, the tension in a string can change instantaneously. But the spring, the force transmitted by a spring cannot be, does not change instantaneously. It takes some time, it is slow, it is sloppy. Then another thing is we are always talking about light springs. That is, the mass is negligible. String is also light. Negligible mass, we are saying. Now, because of this assumption, the force transmitted by the string is the same everywhere, by the string or a spring. Suppose I have a string here. If I say the tension here, the pulling force is T2 and T1, I can say T2 minus T1 is mass into the acceleration. If the mass is negligible, T2 equals T1. Even if I take one portion of the string, the same thing holds good. Supposing I say this is T1 and where I have cut it, let us say the tension is T3. Since the mass is negligible, I'll get T3 minus T1 is equal to mass into acceleration. Mass is negligible, so T3 equals T1. That is equal to T2. So the tension is the same throughout the string if it has got negligible mass. Same is true for a spring also, a light spring. The force of tension or compression is the same throughout the spring by the same logic. Now we will take up some interesting problem to understand this concept. Supposing I have there is a block suspended from the ceiling. This is a string, and now here there is a spring, and both are having, say, masses. Let us say m1, and let us say this is m2. There is a spring, and there is a mass here. Well, we wish to know what will happen if we cut this string here. This is actually a JE problem. What will happen if we cut this string here? Now, before we cut it, what is the free body diagram? The free body diagram is M1G for this and the tension. I will call that as T1. In the spring, the tension would be T2. So, you would have M2G. The spring will be elongated. The string will get pulled, so it will pull back. You will have T2, and here you are going to have T2 again, the pull of the spring T2, pull of the spring on M2 is T2. So initially this T2 will be equal to mg at this situation, and T1 is going to be equal to T2 plus m1g. T2 is m2g, so it will be m2g plus m1g. That will be T1. This is how the situation is before you cut it. When you cut it, what happens is this tension in the string immediately becomes 0. But this tension T2 of the spring does not become 0. It does not become 0 because, as we said, the string is already in an extended state and it takes time to change its distortion, get compressed and become reduce the forces. So because it is sloppy, because it is slow, T2 is still m2g. So what will be the acceleration? If you see the acceleration, now you draw the free body diagram, T1 has vanished, you have T2 and m1g. T2 and here you have T2 and m2g. T2 is non-zero. T2 is not equal to 0. In fact, T2 will be equal to mg, non-zero, and it will be equal to T2 will be mg. T2 will be mg. So T2 is going to be mg, m2g rather. T2 would be m2g. This will be equal to m2g. So what is the net force on m1? The net force on m1 is m1g plus m2g, and divided by the mass m1 will give you the acceleration. That is the acceleration of m1. A1 would be m1 plus m2 by m1 into g. You find that the acceleration is greater than the acceleration due to gravity. Here, because the net force is 0, T2 minus m2g is equal to m2 A2. T2 is still m2g, so m2g. So m2 into A2, you will have A2 equals 0. So after you cut the spring, this will have 0 acceleration. This m1 would have an acceleration given by m1 plus m2, m1 plus m2 by m1 into g. If m1 and m2 are equal, then you will have 2m1 by m1, m1 cancels, you will have a1 equal to 2g. That is, this will accelerate downwards at twice the acceleration due to gravity, and this will have zero acceleration. Let's take the same problem but with strings. See what happens. Supposing I do this with both, I replace the spring by a string. Now see, a very interesting thing happens. This is the thing, this is M1, and I have shown instead of a spring, I put a spring. Now if I draw the free body diagram, I have M1G, I have T1, and here I will have T2, the pull of this lower string. This is M2G, and this is T2. That is T2. Now let us say I cut this. If I cut this, I can surely say the tension in that string is 0. Yes? Now I want to find out the acceleration. Now because this is a string, I know initially T2 was equal to mg, m2g. So, but after I cut the string and the situation changes, I am not sure whether T2 will still remain m2g, because the tension in the string can instantaneously change. So therefore, I will say, let us say it has become some T2 dash and T2 dash. Now let's write the force equation. Let this have an acceleration a1. Let this have an acceleration a2. So what can I write for this one? For this one I can say m1g plus T2 dash is equal to m1a1, and for this it will be m2g minus T2 dash is equal to m2a2. If I added these two, T2 will cancel. I will get m1g plus m2g equal to m1 plus now, although we have said a1 equal a1 and a2, because the string is inextensible, if this moves by x and this moves by x, this will also move by x. If you differentiate this, the velocity will be the same. If you further differentiate it, the acceleration will be the same. So a1 and a2 are equal. So I can write m1 plus m2 into a, where a is nothing but a1 or a2. This is because the string is inextensible. We would not have been able to say that for a spring, because the spring gets elongated. The acceleration at the two ends of the spring need not be the same, but for a string it will be the same, because we are assuming that it is inextensible. So m1 m2 cancels and a is equal to g. So now if you take the first equation, substitute a1 is a, a2 is a. If you substitute a as g, you will have m1g, you will have m1g here, m1g cancels, and you get T2 dash equal to 0. So the tension which was T2, which was initially m2g, has instantaneously, as soon as you cut that, has changed to 0. Let's take another question, interesting question. Let us say we now have two springs and a string going around the pulley. I have a pulley here and mass. This is 2 kg. There is a spring here. This is 3 kg. Here there is a 1 kg mass. There is a spring, and there is a 4 kg mass. Okay. So the system will be in equilibrium. 3 plus 2 is 5. Springs and strings are like. 3 plus 2 is 5. 4 plus 1 is 5. I will call the tension in this as T1, tension in this as T2, tension in this as T3. There are three elements other than the blocks: string, one string and two springs. So T1. Now let's draw the free body diagram for this. If you draw the free body diagram for this, you will have for this 40 and T1. For this block you will have 10 kgs, 10 newtons downward, then T1 downward, and you are going to have T2 upward. If you come here to the 2 kg block, you will have T2 upward, 20 kg, 20 newton downward, T3 downward, pull. For the 3 kg, you will have T3 upwards and 30 newton downwards. So, what do you have? T1 will be 40 because the system is in equilibrium. So, if T1 is 40, 40 plus 10, this is 40, 40 plus 10 is 50, T2 is 50. Okay, and here T3 will be 30 because it's in equilibrium. T2 is 30. So if T3 is 30, so if T3 is 30, T2 will be 50 as we got here. So that is the free body diagram and the values of the forces. Now what we are going to do is we are going to cut this string either here or here, anywhere. Either here or here, we cut it. Now you cut that, T2 will instantaneously become 0. So I have put T2 as 0. T2 becomes instantaneously 0. Okay. Now see, we would like to know the accelerations of these bodies. So now if you come to 3, see what happens to 3. If you take 3, this is T3 and this is 30. So T3 is equal to 30. T3 doesn't change. So therefore the acceleration of the 3 kg block will be 0. I will call this as A3. This is A1, A2, A3 and A4. So A3 will be 0. Let us come to 4. If you come to 4, here T1 will still be 40 because it is a spring. So therefore this will be 40, 40. A4 will be 0. Let's come to the 1 kg block. This is the 1 kg block, 10 newtons. You have basically T1 remains 40 because the spring is still in an extended state. So the net force is 50 newton downward. And the mass is 1 kg. Yes, mass is 1 kg. So this will be 50 meters per second square, or roughly it's 5g. This will have an acceleration of 5g. Come to this will also have an acceleration of 5g. 30 plus 20, not 5g, 30 plus 20 is 50, and this is a 2 kg, this is A1 or the 1 kg block. A2 will be 50, 30 plus 20, 50, and this 2 kg by 2 kg, that will be 25 meters per second square. That is nothing but 2.5 g. So those will be the accelerations. Thank you.